Thank you very much for having me here in this IBO workshop. It's my pleasure to come and give a presentation on some of the works. Sure. Yeah, thanks. Anyway, I'm Pradeep from Energy Research Institute at Nanyang Technological University in Singapore. My PI is Prof. Wan Manpun, and he's the associate professor in mechanical and aerospace engineer in NTU. So today I'll be briefly talking about our implementation for multi-system model predictive control in one of the commercial buildings in Singapore. I think this is a slide that we are very familiar with already. It's basically a survey by McKinsey in 2017, actually almost 7 years ago. And he identified some of the actionable areas for optimizing the energy systems, which has the most potential for optimizing the energy systems. And buildings, not surprisingly, were one of the most, let's say, objected areas which has a significant potential for the optimization. In Singapore, they have set a very ambitious target of reducing the total carbon emission by up to 36% compared to the levels in 2005. I'm not sure whether by 2030 we are going to achieve that target or not, but that is the policy set out by the Singapore government itself. Let me briefly introduce to you the problem statement with the conventional or the current systems that are employed to control various systems in the building in Singapore. Usually in Singapore you'll find PID or the reactive control systems. The problem with PID is that they are not able to do the prediction and optimize your building for multiple controllable systems. First thing is that in the buildings you have multiple systems. For example, your ACM-based systems, your lighting systems, and similarly your shading systems. Generally, all three systems are controlled in a separated, segregated manner. What I mean is that they are not coordinated control. I mean, you can imagine a scenario in Singapore where it's very hot and humid, and then you have, let's say, in case you have a very favorable weather conditions, you can maybe open up your curtains and let in the daylights, and thereby reduce the lighting power requirements inside the buildings. But most of the cases in Singapore, I mean, where the weather is really hot and humid, when you open the curtains, you let in a large amount of solar heat gain as well, and thereby you add in the heat load to your ACMV systems. But again, like when you think in terms of the optimizing the building energy systems, you need to have a very coordinated. You need to think in terms of all these three systems, right? For example, what would be the optimum amount of the level with which you need to open up your curtains? What is the optimum settings for your lighting so that it's not visually impairing for you? And similarly, the total, like when you set your lightings and shading systems in such a way, what would be your impact on your ACM-based systems? If you open your curtains up more, you are introducing more heat from the outdoor, and then as a result, you are adding into your ACM-based systems. So the problem we are trying to address is how to optimize all these three systems in a very coordinated manner such that you end up saving energy as much as possible, but without compromising in terms of the comfort of your occupants. So we have multiple control targets in a building. You want to optimize for your energy, but you also want to optimize in terms of your occupancy comfort, in terms of the thermal comfort, and in terms of the visual comfort for your users. So the current challenge with the PID system is that they are not able to do any of these They are not able to respond to the transient disturbances. As a result, you have, whenever you have a PID control, you have a fluctuating between highs and lows conditions, whether it be in terms of thermal or whether it be in terms of the visual comfort. So that is where our MPC or the model predictive control comes in. So when you, as you can see here, there are multiple systems in the building that you want to control, and you have to operate your control system within certain constraints required by the building or required by the users. And then you have multiple disturbances that are acting in the building, which your typical PID systems, PID control systems are not able to account for. So in terms of like a predictive model, you can have a white box model or a purely physics-based model, but on the other end of the spectrum, you can have a black box model or the data-driven models using the various AI or ML algorithms. Similarly, you have multiple targets. You want to optimize for energy. You want to optimize for in terms of the comfort of your occupants. And there are various ways you can do the optimization. So far in our deployments, we have started out with the physics-based model, and then gradually we have progressed to the adaptive, the machine learning-based MPC model. So this is I'm sharing some of the results that we have obtained for one of our deployments in BCA Skylab. So BCA is the Building Construction Authority of Singapore, and they have this specialized laboratory facility which consists of like two equal rooms. One is the test room, another one is a reference room, and they are both receiving a very equal heat load in terms of heat load and other loads. So in here, we can actually do a side-by-side testing of a typical conventional BMS system in Singapore versus the model predictive control system that we have deployed in one of the test rooms. So as you can see from the first figure, which is the variation of room temperature for a typical day in one of our test cases, when we have employed the PID for BMS, we are seeing a very fluctuating temperature within the room. But when we do MPC, due to our forward prediction of various disturbances coming into the building, we're actually able to maintain the condition in a very steady manner. So the second figure, if you look at how actually the hardware is behaving in terms of a conventional PID control versus how it's behaving in terms of MPC. So usually for your PID, you have like a time control of these hardwares where your reactive system is measuring the temperature inside the office space and then reacting to whatever the thermal load that has occurred inside the building. So it's always swinging from highs to lows in case of the PID-based BMS control. Whereas for your MPC, you are actively controlling your actuators so as to provide a very steady and stable indoor condition for your occupants. So you have very minor fluctuations in terms of MPC, which is why you get all those steady conditions inside the room. And if you look at the third graph, which is the thermal comfort index, or the PMV as we know it, the predicted mean vote. So obviously the optimum conditions is 0, which is the thermal neutral value for the PMV. In case of BMS, you can see that the thermal comfort is varying from comfortable to not so comfortable zone. And in case of MPC, you have a very steady thermal comfort index for your occupants. And this is how MPC is able to save energy by actually minimizing the energy wastages that typically occurs in your conventional PID systems. So we talk about the multiple systems, multiple controllable systems in a building. So here we are controlling in this case, in this building, we have the dimmable lightings, and then we also have a shading system based on the electrochromic glass. So you can control the tint level of these shading systems so as to provide the optimum level of daylight for your buildings. We are measuring also. We are also measuring in terms of the glare probability or the amount of daylight coming into the building, and using the tint level of the shading system, we can actually actively control the amount of daylight coming into the building. So when we measure daylight glare probability in Singapore, the constraint is that the DZP should be within 0.35. As you can see, for the typical BMS, it's not able to constrain within this 0.35 of DZP. Similarly, if you look at the illuminance level inside the room, then the typical allowable constraint in Singapore is that the illuminance should be within the 500 to 3000 lux level, but as you can see for BMS, it often violates that constraint. So MPC is able to maintain within these constraints now. Now we come to the multi-system and the multi-zone implementation at one of the commercial buildings in Singapore. This office space, this space consists of like the office spaces for the office workers, plus some of the learning zones for the students from the civil service scholars. Here we are doing the coordinated control of the multiple systems such as ACMB lighting and shading systems, and we are optimizing in terms of the energy and the thermal comfort and the visual comfort. So this is the typical ACMB systems in these spaces. So we have the fresh air, and then we have the chill water based FCU systems. And we have installed various sensors for the comfort measurement for various parameters in the ACMBs. For the lighting systems, we have installed some of the LED lights with the dimmable drivers, so we can control the optimum lighting level inside the office spaces. So for the blinds control, we have installed the motorized shading system. This is the the LDR camera setup to measure the DZP levels inside the office space. So when we talk about the multiple systems and the multiple targets that we need to meet, so in terms of the ACMB, we are trying to optimize. The first parameter we are trying to optimize is the total cooling energy that is required to provide the optimum comfort level inside the office space. So the second target is, of course, to minimize the discomfort for the occupants. So to integrate to develop further into the multiple systems, in terms of the lighting and shading, we are trying to minimize the amount of heat gain from the windows, and we are trying to minimize the lighting power requirements inside the building. And all the while, we are trying to constrain, we are trying to achieve the allowable visual constraints required for the typical office space. This is the occupancy-based trigger systems that we have implemented together with MPC. So based on whether the rooms are occupied or not, we trigger the MPC accordingly. This is something that we have done for this building as well. This is a web-based occupant feedback system. So basically, you as a user, you can control your thermal environment where you are working. So you just need to scan a QR code, and then you can immediately receive some data of your room, the temperature, the humidity, the illuminance, and then based on how comfortable you feel, you can provide the feedback to our systems. So the feedback you provide is accumulated in terms of like a number of votes, like too hot or too cold or too dim or too bright. And once you have a sufficient amount of votes in the room, then it automatically optimizes our algorithm to bias according to the comfort requirements that you need. This is some of the high-level results that we have obtained from this. So as you can see, the typical BMS is always overcooling, and our MPC is able to constrain to thermally neutral conditions, which is where we save a significant portion of energy. This is some of the statistical results for the comfort conditions, the various temperature, and the cooling power. So you can really see that by significantly cutting down on the energy wastages that occurs during using a PID-based conventional systems, we are able to achieve a significant portion of energy. These are some of the results for the MPC with user feedback control. So as a user, once you provide the feedback, typically in Singapore, because it's a very hot and humid climate, so once you come from the outdoors to the inside, you are in immediate requirement of a lot of cooling for yourself. For example, when in the morning when you start in your office, typically you feel that the optimum, the PMV0 is not sufficient for you, so you need to cool a bit more. So you provide the feedback and our MPC is able to bias our system to provide the optimum cooling for you. Similarly, this is some of the results for the lighting and the shading and the shading control, and how our MPC is able to basically provide the lighting requirements within the allowable constraints for the building. So overall, our MPC, when implemented without the feedback system, we are able to achieve up to 33% of ACMP energy savings. But when you have a feedback, because in Singapore you typically you feel like because it's a hot and humid climate, you want to have a more cooling. So once you have this kind of feedback integrated together with our MPC, our savings were reduced to typically about 24% compared to the conventional BMS system. So this is the overall implementation summary of our MPC. In all our deployments, we have been able to achieve from 20% to up to 60% of energy savings. This is briefly about where we are going in the future. So currently we are at the buildings.
Yeah. So can you quickly finish these slides?
Sure. Yeah. Yeah, so currently we are at the building level. In the future going on, we have the grid people working on to optimize the grid systems. And what we are trying to do now is to integrate the buildings with the grid system so as to develop the building to grid interactions. Again, this is the same like what our research plan is going into the future. So from the buildings, we want to go to the urban city energy management system. Thank you. Yeah, that's sorry.
Okay.
Sorry for
Very good. Let's
taking
thank our speaker.
a bit of time. Yeah.
Do we have one quick question for Pradeep?
So your cost function, right, which includes energy and the comfort and
Yeah.
How do you determine the weights of the cost function of the different terms?
The weight is usually based on our experience or based on our hit.
So it's based on some
trial.
heuristics?
Yes, yeah. So we tried a few different combinations, like how we want to optimize the building environment, whether we want to optimize in terms of the energy or whether we want to optimize in terms of the comfort level. So based on that, we played around with a few of the numbers. So that's how we came up with the weight factors for different parameters in our optimization.
So just a quick question too. So you have good savings, right? But you have some significant implementation costs, right? Do you have any idea? It costs you a lot to implement this strategy.
Yeah, definitely.
Right? So do you have any idea about the overall economics of this?
Yeah, so definitely, I mean, like this is a research project. So, I mean, with whatever the constraints of the budget available to us, we went on and tried to implement different kind of sensors, different kind of actuators into the office space. So we realized it's not like a scalable options for the future, going into the future. But from this project, we have been able to learn a lot. And then and with various tools, machine learning and AI tools, we have been able to optimize our systems to the point that where we don't require all of these sensors. So in terms of cost, we have been able to optimize a lot. And for our future projects, we are looking at the ROI of the approximately 3 to 4 years. So that's where we are at now.
Target. Okay.
Yeah.
Thank you.
Yeah.
Very good. Thank you, Pradeep.
Thank you. Thank you.
Come on up.